Okay, let's talk about chaos. Ever looked at something like a turbulent river, a plume of smoke, or even stock market data and just seen a total mess? Well, finding clear, repeating patterns in these complex systems is a huge challenge. But what if there was a special tool, a kind of decoder, for that chaos?
Take a look at this. What you're seeing here is a single moment in time, a snapshot of the pressure inside a turbulent jet. You know, like the exhaust from a jet engine? It's a whirlwind of activity, right? It looks like pure random noise, with no rhyme or reason. So that leads us to the big question, doesn't it? How in the world can we make any sense of this? Is there a way to reach into that mess and pull out the most important, the most fundamental structures that are hiding in there? It's kind of like trying to hear a single violin in a completely chaotic orchestra. To do that, we need a very special kind of tool. You can think of it as a mathematical decoder, one that's been specifically designed to find the real signal hiding inside all of that spatial and temporal noise. And that decoder? It's called SPOD. So this is it. SPOD stands for Spectral Proper Orthogonal Decomposition, and it's a way to find the most dominant repeating patterns in data that's changing all over the place, both in space and over time. And it's not just some random method. It's built on a really powerful mathematical idea called the Carhoonen-Loewe theorem. That theorem basically guarantees that SPOD finds the most efficient way to represent all the energy or activity in the data.
Yeah, here's the crucial part. SPOD doesn't just find any old patterns. It finds the most important ones. And it does that by figuring out which structures contain the most energy, and then it ranks them. So we get this beautiful hierarchy of the most significant building blocks of the entire system.
Okay, so how does this decoder actually pull off this magic trick? How does it take that absolute mess we saw at the beginning and turn it into an ordered list of clear structures? Well, let's pop the hood and look at the engine of the algorithm.
The real magic, the secret sauce, is in that first letter, S for spectral. See, instead of trying to look at the entire chaotic system all at once, which would be incredibly difficult, SPOD uses a really clever divide and conquer strategy.
The best way to picture this is to think about a prism. You shine a beam of white light into it, and it splits that light into all its individual colors, right? Its fundamental frequencies. Well, SPOD does the exact same thing, but for data. It takes a complex signal and decomposes it so we can look at the system one frequency, one color, at a time.
Now, the mathematical heart of this whole process is something called the cross-spectral density, or CSD. For each of those colors or frequencies, the CSD basically measures how the wiggles and waves at one point in space are related to the wiggles and waves at every other point. It's the key that lets us find those big, organized patterns.
And to get a really clean measurement of that CSD, we use a brilliant process called Welch's method. First, you just chop up your long stream of data into smaller, overlapping chunks. Then, you apply a window to kind of smooth out the edges of each chunk. After that, you convert each one to see its frequency colors. And finally, and this is the most important part, you average all those chunks together. That averaging is what filters out all the random noise, leaving you with a clean, reliable picture of the system's real patterns.
And this diagram right here just illustrates that whole workflow perfectly. You can see we take our raw data, we chop it up, we transform it, and then we rearrange everything by frequency. This is what lets us mathematically sort through the CSD at each frequency to find and then rank those most important patterns, those hidden structures we've been hunting for.
But here's the thing. Using a powerful tool like this isn't just about pushing a button. It actually involves making a really critical choice right at the start. It's a fundamental trade-off in how we decide to estimate that spectrum.
And that choice really boils down to this one question. When you're looking at your data, do you want a picture that's super detailed and sharp, but maybe a little bit noisy and uncertain? Or would you rather have a picture that's smoother and more reliable, even if it's a bit blurrier on the details?
Let's look at a real-world example from a wind turbine wake. Over on the left, we used long chunks of data, and you get this fantastic frequency resolution. Look how sharp those peaks are. The problem? Well, see that big gray area? That's our confidence interval, and it is huge. We're just not that certain about the exact energy levels. Now, look at the plot on the right. Here we used a lot more chunks, but they were much shorter. The result is a way smoother spectrum, and that tiny gray band tells us we're much more confident in our answer. The trade-off, though, is that we've lost some of that fine detail. The peaks are a little broader, a little blurrier.
So, at the end of the day, you're faced with this classic analyst's dilemma, this trade-off between bias and uncertainty. If your goal is to tell two very closely spaced frequency peaks apart, you've got to use long segments. But if what you really need is a statistically solid, confident answer for the energy at a certain frequency, then you need to average over many short segments. There's no single right answer. It all depends on the story you're trying to find in the data.
All right, enough theory. Let's get to the payoff. We've gone through the process, we've made our choices. What does SPOD actually reveal when we point it at that real-world chaos?
Okay, let's go back to our turbulent jet. This is its energy spectrum. Each of these lines represents the energy of a different ranked pattern across all the frequencies. And whoa, look at this. Right around a frequency of 0.6, there is a massive gap that opens up between that top line and all the others. That is a huge clue. It's screaming at us that, at this one specific frequency, a single pattern is just completely, overwhelmingly dominant.
And there it is. The chaos from our very first slide resolves into this beautiful, coherent, organized wave packet. SPOD has literally pulled the signature of a classic Kelvin-Helmholtz stability right out of the noise. This is the fundamental physical mechanism driving the jet's behavior, and it was completely buried in that raw data.
Now for something completely different. Let's look at the wind turbine wake. The spectrum here is totally different. Instead of broad humps, we see these incredibly sharp, distinct spikes. That's the telltale sign of something periodic, something tonal. And sure enough, these peaks line up perfectly with the frequency of the turbine blades passing by, and all of its higher harmonics.
But what's really fascinating here is that the modes are telling two completely different stories at the same time. Down at the bottom, at that high blade passing frequency, we see exactly what you'd expect, little vortices getting shed from the individual blades. But up top, at a much lower frequency, SPOD uncovers a much larger, slower instability, this massive vortex street that's caused by the entire turbine acting like one big object. That's a huge global pattern that you would never ever see just by looking at the raw data.
So, what's the big picture here? We've gone all the way from chaotic, messy data, we've run it through this mathematical decoder, and we've come out the other side with clear, physical structures. Let's just bring it all home.
You know, the key takeaway is really this. SPOD isn't just some fancy algorithm. It's a powerful lens. It lets us look past all the chaos and actually see the hidden physical story that's going on underneath. It turns a wall of messy numbers into clear, actionable insight.
So, a technique like this can turn what looks like random turbulent noise into a clear story about physical instabilities. And it really makes you wonder, doesn't it? What other incredibly complex systems, everything from climate science and weather patterns to the ups and downs of the stock market, are just sitting there waiting for us to apply the right decoder to finally understand what's really going on?